we had this fellow, and he he criticized the scientific method that we have here. He doesn't like it, and he went over different aspects of it, and we're going to answer some of his inquiries, his questions, right? And here's one. Okay, this is what he said. He was talking about whether science is about studying, and whether science has to do with knowledge, and whether you test a hypothesis, as we covered the other day, but then whether these science is about getting a degree. Is that what science is about? Studying, getting a degree, collecting knowledge, and learning from our mistakes? Is that what it is? Is science an ongoing process? Okay, and here's what he's had to say, his own words. Okay, so here it is. Pay attention. Give me a second here. Here it goes. The questions and issues addressed in this rebuttal include: is science about learning by rote? Is science about accumulating knowledge? And does science progress through trial and error?
To graduate, you need to show that you have an understanding of what you have been taught. Now, to answer the question of what happens if you obtain no knowledge, well, that's a tricky one, because you should obtain at least a tiny amount of knowledge. Even if the knowledge that is obtained is the thing you are doing isn't working, that is still some knowledge. Yeah, it may not necessarily be the knowledge that you're after, but science is all about trial and error. If something doesn't work, well, you now know that it doesn't work, so go back to the drawing board and try something different. It is very difficult for me to think of a scenario in which you wouldn't actually gain any knowledge, unless of course you're doing absolutely terrible science.
Terrible science. Yeah, I agree with him. Terrible science. What is terrible science? Well, let's find out. I don't know where this fellow studied. Maybe he studied at Harvard or Cambridge, one of those monasteries, and maybe he was a choir boy. He was required to memorize everything that was fed to him, and that's what he regurgitated. Let's find out what terrible science is. Okay, so he says terrible science is, or we say here, terrible science is what he mentioned there. Graduates must show that they can regurgitate what they memorized by rote from the previous generation. Is that what science is? You sit down, you open a book, you memorize what's in the book, which is what people from the previous generation wrote. You memorize it, regurgitate it for the test, get a degree. That's science? Studying, memorizing? Is that how science progresses? Is that what he calls studying? Just memorizing? Science, he says, is knowledge. We say it's got nothing to do with knowledge. Now, people raise the issue, the argument that that's what it's always been. The word science comes from the Latin meaning sire, meaning knowledge. And the question is, first of all, etymology has, we don't use that in science because that's just history. That's just, the origin of a word. They could have misdefined it from the start. Okay, that's one issue. The other one is that, we change definitions whenever we find something wrong with them over the ages. We don't rely on history and say that's what science was from the beginning and that's how we have to keep it today. In fact, in the 17th century, they changed the notion of science, which they called natural philosophy, and they said, look, there was a problem with the Greeks. What was the problem? Well, the problem was that they didn't run experiments to test their hypothesis. Okay, so the Greeks did not test the hypothesis, and so they changed the notion of science. They say, no, science, you need to introduce experiments, and you have to emphasize math. You need to have equations and so on. And so they changed the direction of science in the direction of math, and what they did was describe the experiments that they ran and come up with an equation. They say, okay, that's science. Science is an equation that describes how something occurred, meaning what happened, but only a description of it. Mathematical, a quantitative description of it. And to this date, we have no explanations. That's the problem. Okay, we have no rational explanations for any phenomenon, especially that's invisible, intangible. Okay, that's where we're at. So it doesn't matter that the etymology takes you back to the word Syria, which is knowledge, if we redefine words when we find something wrong with them. And the question is whether knowledge has anything to do with science. And no, knowledge, when you know something, you believe it. The other guy believes something different. You believe that God exists. You know God exists. The other guy knows that God doesn't exist. So who's right? Which one is the fact again? If everybody knows things which are opposites, contradictory. And then no, we don't do trial and error in science. Science, we have to explain something. You can do all the trial and error you want in your dark basement. When you come to the conference, we need for you to explain what you learned. what your conclusions are from your experiments. But to do an experiment, anybody can do an experiment. Here, I'll do an experiment, which I always do here, very important experiment. I let go of the pencil, okay, and it falls to earth. There's your experiment. Let's do it twice, so it's repeatable, so it's scientific, right? There it goes again, okay? Now, I did the experiment. Was that science? What did I learn? That a pencil falls? We call that science, doing experiments and describing it quantitatively, like, what the acceleration of gravity is, what rate it fell. Is that science? That's like saying I measure a table, measured 1 meter, 1 meter and 1 millimeter because I measured it more precisely, and you get a Nobel Prize for that because you measured something and put it into an equation. Is that science? So no, science is not by trial and error. It's technology, which is by trial and error. We do not do experiments in science. What we do in science, we explain experiments, how they happen, what caused them to happen. That's what we do in science. But we don't do experiments. The experiment is what the technician or the operator does. He goes and does the experiment, brings the data back to the engineer or to the scientist, and that's the guy that's going to figure out how it happened or what actually happened. But to do an experiment is not science. You go to the lab, you mix 2 liquids, it was blue, now it turns red. You don't understand why, but you did the experiment. And you can see at what rate it went, so many seconds it turned, red or blue or whatever. Is that science? Just, it's what Ernest Rutherford called stamp collecting. Science is not stamp collecting. You don't just collect data and bring it in and say, I did science because I did an experiment and collected all this data and have the equation to show for it. Okay? So here's genuine science in comparison. Okay, science is objective. Its purpose, its goal is to understand how the universe works. For that, you need to understand gravity. You need to understand magnetism, electricity, what the atom looks like. You need to discover. You need to try to explain the invisible world of Mother Nature's and Father Universe's. You can't. It's the visible stuff and tangible stuff that we have figured out. We haven't figured out the intangible, invisible stuff. That's where the problem is. And in science, we must explain and regurgitate what the previous generation feed us is not science. Okay. So let's get science right on the right track. What this fellow was doing was not science. What he said is science. That's not science. Okay. Here we have examples of that. Here's gravity, according to general relativity. Is this science? Okay. We have the Earth and the Moon flying around it, and they're both going around the Sun. Okay. And so why doesn't the Earth fly away? And so the answer that these people give you is that time is warped, or what this fellow said the other day: time is bent. Okay, so time is bent. What are we saying? Bending the seconds, the minutes, the hours? So we have a problem because this is an irrational explanation that general relativity has and which has fed to the world. This is not rational at all. So this is not an explanation. It's not a physical interpretation for how gravity works, how the universe works. Okay, here's a light. Okay, what is light? Well, they say it's a wave packet. Okay, what's a wave packet? And this is what they draw. This is what they show you. This is a wave packet. You're staring at it. This nonsense, this little squiggly little thing that moves. What is that? What are we staring at? Okay, what is this nonsense? But this is the way they illustrate it. Okay, and just in case, if you don't believe in this, you can go always to the Nobel Prize winners. And here's a Nobel Prize winner, and his name is Roger Penrose. He won the Nobel Prize the other day. Okay, and what did he draw? He's the guy who invented the Penrose staircase, by the way. And he draws this in his book, a wave packet. That's where I got it. Got it from his book. That's a wave packet. What is that? Robin Hood's arrow with a squiggly whatever around it? That's a wave packet? Is this what light is? I mean, show me the mediator of light. And they say it's a wave packet, and that's what they draw. It's ridiculous. But this is what people swallow, and they say, oh, it's okay. I have no problem with it. Here's the atom. Okay, this is the one that they use, the planetary model. They have 3 quarks in the center there, held by gluons, which are bed springs that are somehow vibrating. They have this blue electron ball going around, and it falls from one level to another and rises from one level to another, energy levels, whatever those are. And the question wasn't, why does that little blue ball fly away spontaneously? Why doesn't it fall to the nucleus? I mean, it doesn't do either. It just goes from one level to another, back and forth. What, by miracle? I mean, what's the explanation for it? That's what these people have to answer. Okay? And no, they just feed it to you, and people believe it. And they have to use that model to explain, for example, electricity. Because what is electricity? Well, here it is. You see electricity also. There it is, the explanation. It's a bunch of electron balls, okay, that fly from one atom to the next. So if this is electricity, you have to rely on the planetary model, which I just showed. Okay, and again, the question is, why doesn't the electron spontaneously fly away? Okay, that's what you have to answer. If you cannot answer that question, you don't even have a starting point. You cannot even begin your presentation and say, look, let me explain electricity to you. Let me explain ionization to you. Let me explain the quantum jump to you. You cannot do any of those because you're going to rely on the planetary model, which you, at the end of your presentation, say, oh, by the way, we don't believe in our own planetary model. That's not the model of the atom. Then why did you use it to explain electricity, quantum jump, and ionization? Why did you use that model? Show me the real model. Show me your atom before you begin. After all, a lot of people out there claim that they photographed and filmed with the atomic force microscope, with the scanning electron microscope. They filmed and interviewed every single electron, every proton. So if that's the case, you should not have any excuse not to draw, to illustrate for me an atom. A hydrogen atom will do. All I need is to see your little atom. Is it a proton with a little electron bead next to it? Is that your atom? Okay, and then you can't say, well, we don't know what it looks like. We've never seen that far. Well, you did or you didn't. You either filmed it and photographed it or you did. That's one issue. The other one is, okay, so even if you filmed and photographed it, just explain to me why the electron bead doesn't fly away. That's how simple it is. And finally, here we have magnetism. And for that, we have to look at what this fellow from UCLA, he's a professor. Okay, he's a PhD. Okay, that's what you're going to be listening to. And he's going to explain how a magnet attracts another. He's going to boast because they know it all. Okay, so what is he going to explain? He's going to explain that the electrons in each magnet, spin in the same direction. That's what he's going to say. Okay, even if that's the case, how does that produce attraction between two magnets or repulsion between two magnets? That's the issue. So let's hear him first, okay? You'll hear his own version. I sped it up here, okay, just so that you can listen to it in fast motion. Here it is.
One magnet either repels or attracts another, and nobody knows why. Except you, after watching today's video. One way to understand magnets is through magnetic domains. It was discovered that electrons had a property called spin. That is, the electron was spinning as it circled the nucleus. It's the alignment of these electrons' spins that results in the magnetic properties of iron. These atoms have an unusual double valence, in which their two valence electrons are paired with parallel spins.
In summary, a magnet is a collection of microscopic crystal domains that have their electron spins aligned. This is particularly prevalent in iron, nickel, and cobalt, in which there is a pair of valence electrons with their spins aligned.
I like how these people are so arrogant. They know it all. They know it all, and they talk about spin, when first, spin is not spin. Okay? Particle is not a particle in quantum mechanics. They use these words like particle and spin, and people say, well, I know what a particle is. I know what a spin is. It's like you spin a top. No, it ain't. The spin in quantum, they don't even know how to define it. They just say it's a property of an electron. That's all they say. But then they use the word spin when they're trying to give you an explanation like this one. They say, well, it spins. The atoms, and you say, okay, I understand what spin is. No, that's not what it is in quantum mechanics. Spin is not like a top spinning. Okay, and so they use these words and they mislead the public. And they mislead even the students, people who are going to graduate in quantum mechanics and whatever. And so the particle is not a particle because it's not the classical particle. It's not a little ball, which is what they illustrate and move around. Then they say, well, a particle is not a particle. A particle is a wave function. What do you mean it's a wave function? What is a wave function? Yeah, it's a collapse. It collapsed. And then it spins. What spins? You mean it twirls around? No, that's not spin in quantum. What is spin? Oh, we don't know. And so he uses spin, and okay, let's concede. Let's concede. So the electrons are spinning in this magnet, in this other magnet. How does that attract two magnets? And here's the analogy, okay, here. This is the analogy. You have a wagon, two wagons really, and the watermelons are spinning in the same direction. Tell me how that attracts the two carts together. Okay, here it is. Okay, so you have the watermelons, okay, and they're spinning. Okay, great. They're spinning in the same direction. From above, you can say they're spinning clockwise on both carts. How does that bring the two carts together? That's what I want you to tell me. You don't like them spinning in the same direction? Okay, we'll make one of them spin in the opposite direction, if that helps at all. I don't know. You tell me. So how does that bring the fact that the watermelons, the electrons are spinning in each magnet, how does that attract or repel two magnets? What is the mechanism? To say that, the electrons are spinning and brings two magnets together, you don't have a mechanism. And so, these people say, we know it. We know. They use that word know. It's a fact. We proved it. We have evidence. And then they come up with this nonsense. They say, well, the electrons spin in each magnet in the same direction. Okay, so they spin, assuming electrons are particles, assuming they spin, none of which is true, because particles ain't particles and spin ain't spin. Okay, let's concede. And how does that bring the two magnets together? And yeah, you can wait 100 years for it. So these people, they talk about, knowledge that they know and that they've proven through experiments, that they tested the hypothesis, and then they come up with this irrational poppycock. Okay, so you tell me if they have the right scientific method.